That's what I was supposed to do, talk about my experiments. Anyway, so I was from the University of Marseille in France. I retired 6 years ago. And now I have my own personal lab. I didn't think about putting a picture of it because it would be interesting. It's a wooden garage, a Hewlett-Packard style. There is hope. And so it's 36 square meters. Anyway, I'm trying to kill a large number of birds with one stone. I don't know if I'll succeed or not, but I'll try. Anyway, so let's see. So I'm doing two types of experiments, two goals. One is scientific, because I'm a scientist, you know, I like science. And the other one is technology, applications of the field to technology. So let's see, for science. Okay, I do electrolysis. I told you I don't like electrolysis, but I do it anyway. And looking for excess heat. I learned electrolysis with Georges Longchamp in Grenoble when I was working with him for several years. So I know a little bit about it, enough to do what I want to do. And I'm looking for excess heat and also transmutations. I talked about transmutation a couple of days ago. And also I'm doing plasma discharge, thanks to George Egerle, who gave me one of his systems that now it doesn't have any, so I have the only one available on the market, or maybe there's another one. And with microwaves, we can do transmutation, which is very exciting also. I don't know, maybe that will help one day to clean up all the nuclear waste we have. Electrolysis. I was lucky to talk to Stan Pons about the ICARUS 9 experiment, because in 1996, I think that was his last conference he went to, he mentioned this experiment he had done with ICARUS 9 calorimeter and with heavy water and palladium. And he had observed a lot of excess heat. And by the way, that is the one, he gave me one of these electrodes that showed presence of anomalous silver. Maybe it is silver, maybe not, I don't know. Anyway, that one I used. So I have this calorimeter. It's a heat flow calorimeter. Actually, you see at the bottom, it's a Pyrex tube that goes inside this aluminum case. And there are 3 levels of measurements. Let me see, let me try to explain you better. There is a, oh, what did I do? This thing goes too fast. Okay, here you have a, oh, is the microphone working? Yeah, well, okay. Here at the middle, you have a Pyrex tube where you have the electrodes. It's not represented in this picture, but you have the electrodes. It could be a 10-centimeter long electrode, cathode around it with a platinum anode around it. Put heavy water up to here, maybe. And then you can heat it up, you can run it, and you can measure temperature inside the cell with a thermistor, and also you can measure temperature at 3 levels, because there is an insulating layers, and you measure temperature inside and outside. There are 2 levels every time. So by measuring all these temperatures, and depending on the power that's available, you will be sensitive to low level here, medium level here, and high level here. And depending on the quality of this insulation, you can run it at various powers. Obviously, if the power is too high, at one point the vapor will go away. But the good thing with this system is that you can have continuous boiling experiments, because I realized there was more excess heat at the boiling level than at lower temperatures. So I have such an equipment thanks to industrial heat. And I've run experiments, but at the moment it is standing. As I told you, I have so many birds to kill that I don't know which one to choose sometimes. Microwaves. So microwaves is a great thing. This is thanks to George Egerle, who worked a lot to develop this technology and find the right system that works. It's a kitchen microwave generator. When it breaks, I buy a used one for 20 euros and take the, unfortunately, there are only 2, 3, 4 models. They're all almost the same. It seems like they're all coming out from the same factory. And at the beginning with George, I wanted to do calorimetry with that, but I realized it was too complicated, so I gave up and focused on transmutations. This is it. You see, this is a cylindrical chamber. It is adjusted to the wavelengths of the microwave generator. And inside that you put a sphere, a quartz sphere, with, oops, okay, I'm not good at that. Quartz sphere. This one is dirty because after it was clean at the beginning, but after a few cycles, a lot of deposits that come on it. There are two holes. So when you run it, I mean, you have seen yesterday, showed you, you have a lot of noise and beautiful light. And when people come to visit my lab, if I want to show them something that works, it's better than electrolysis, you know. Or, I mean, they want to see something, you know. I want to see cold fusion. You cannot see cold fusion. You see numbers on a graph, you know. That's all you have to see. This one is more practical, you know. And in the last experiments I've done, I used charcoal powder, though there are impurities in it, but the analysis showed very interesting increases in composition. I mean, there was carbon, obviously at the beginning, but carbon burns, most of it burns with oxygen. And you can see a lot of transmutation events that happen. You know, I don't know what they mean. It's up to you if you have an explanation. I know George has some explanations for that, but you have to be open for explanations. Technology, yeah, now because everybody is pushing for technology. Actually, I would prefer to do science. It's more quiet. There's no IP, no patents involved, nothing. Just do it's very quiet work. But with technology and money, you have. If you want money, you need to technology. That's the problem. I prefer not having it. Anyway, I worked with 3 different fields: nickel nanopowders, nickel palladium zirconium oxide, solid-state electrolytes, and biological transmutations. Okay. Nickel is known not to load. I mean, load at 6,000 atmosphere pressure. And I tried nanopowder of nickel, 20 nanometers. I bought it from a German company. It costs a lot for a gram, but anyway, it's a lot more than gold. And I realized that if you put hydrogen in nickel powder, nanopowder, it doesn't load. At room temperature, no way. Now, what I do, I've done some treatment. First, I remove the moisture, water, by heating in vacuum. Then, I heat in hydrogen to remove the oxide layer, because there's always an oxide layer. I mean, normally. I mean, people say it's dangerous. I didn't find it dangerous. I know some people had problems with it, but I'm immune to nickel, maybe. I'm part of the 90% because of my diet. I'm a vegetarian. That helps. I don't know which one is true, or both. Anyway, I mean, it's not like a powder that goes everywhere. It's very heavy, stays. Anyway, maybe even though it's nano, the grains are not nano. They are just sticking together. You know, it's chunks of metals. And after this treatment, I introduce hydrogen at room temperature. It doesn't go inside. So if I start increasing the temperature, then you see immediately the pressure drop. I measure the loading by the pressure drop. It's quite easy. And you see the pressure drops. And then I increase the pressure again, the pressure drops even faster and faster. It's amazing. And they could go up to 0.43 loading at about 130 degrees C. So this is very important for future applications of using nickel nanopowder. Now, the idea is to do cold fusion with nickel nanopowder. That's the idea, instead of palladium. I have developed a heat flow calorimeter, but it's a Sibectile, but simplified. There is a French writer. His name is Antoine de Saint-Exupéry. You all know his name. He said, perfection, this applies exactly to add, I'm sorry, he's here. Perfection is not when you cannot add something, it's when you cannot remove something. So I'm thinking about add messages. It makes it shorter, better for me. So I've done a heat flow calorimeter with thermocouples. And instead of, I mean, I know that at Storms I've done a very good job in that direction, but mine is simpler, less precise, but very simple. Because I'm using, which one is it? This is the cell. It's a stainless steel cell with a gas tube to put gas in it, hydrogen. And I have 3 screens for heat reflection. The whole thing around it is in vacuum. Up, 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 up. No. and you have vacuum around. Then you have a layer, this is aluminum case, it's a double wall. In between you have an insulating, oh, this thing is, this is a, I have too many nails. This is an insulating layer, I will show you. And then I put 50 thermocouples in series, but only in one direction. Because of the cylindrical symmetry, you don't need to put so many thermocouples. You get the same signal, it's just amplified. So instead of having volts, you have millivolts, but the result is about the same. So I show you now the construction of that thing. Now you can see the two parts with an insulating layer in between and the thermocouples that are attached with ceramics, you know. The whole thing is put in a constant temperature bath. And here, this is a view of the cell attached to a flange. And I have a thermocouple that goes inside, and I can evacuate the powder, and then put, again, hydrogen, and heat it to, so far I went to 600, 700 degrees, but this is stainless steel, and stainless steel has a problem that hydrogen at these temperatures start diffusing out. So in the future, I will go to quartz, because quartz is better. Could stand maybe 1,000 or 1,100 degrees. This is the screens I'm using to lower the power input, to improve the COP, and to better measurements. Now, this is a view of the system. It's in a refrigerated tank, water tank. I have all temperature sensors and pressure sensors. So experiments have been conducted in collaboration with program with Renault and Nissan. As you know, Nissan is working with a number of Japanese universities. And I had a chance to develop this technology using their powder. It's not my powder. So I'm using the same zirconium, palladium, nickel powder. And the first experiment was done outgassing the powder first at 150 degrees to remove the vapor, the moisture, and then putting the hydrogen and heating the temperature. Second was done after heating in air again to remove the deuterium, the hydrogen that's inside for 60 hours at 450, and the third, same thing. So here the first graph that shows you the excess heat measured as a function of temperature. It's the blue circles are the actual measurements with 75 grams, and then I've just calculated I normalized it to 100 grams because this is what they're using as a reference, so you can compare numbers. So you see it's less than 2 watts, and you see an increase with temperature, and the leveling off around 400 degrees, just like Akito said the other day at the conference. So what I did, I removed the powder. You might ask, why didn't I go higher in temperature? Most of the time because the heating filament breaks. You know, that's a very casual problem we have. I removed the powder, heat it in air for 60 hours, and then started all over again. Okay. I'm using 40 watts maximum here. Here's the new curve. It's more interesting, but there is a plateau. I don't know if the plateau has any meaning. It could be in the error bars. I don't know. But you see that I got more than 5 watts, and you normalize it to 100 grams, you get 7 watts. And it seems that now it's going up with temperature, which is very, very exciting for me, because I plan to go to higher temperatures. That means that there is a lot of hope in this technology. Now, after the second cycle, I mean, I am improving by a factor of 3, so I wonder what will happen at the third time, you know? So I was very excited, but that's the problem with cold fusion. You think the next experiment is a good one, you know? Always. Anyway, that's why you're trapped. So this shows you that the experiment lasts for 8 hours. And you might ask, why did I stop after 8 hours? Because I increased the power to go higher, to get more heat. And then the filament break, the heating filament broke, and that was it, you know. That, I'm sorry, it didn't work. Third treatment, as I told you. And now, no more excess. In one way, I was happy. That was a blank. But in the other way, it didn't work. So I have to start all over again now. So you see, it's a very good quality calorimeter. I can work at high temperature. I can do anything I want in it. And I think with a quartz cylinder, a quartz cell, I would be able to go to higher temperatures. Also, using a quartz might give the capacity of putting a coil around it and make some magnetic activation, maybe, in the future. Proton conductors. This is the first experiment I've done back in 1993 when I was at Lawrence Berkeley lab with Gabor Somogyi's lab. That's where I started, following the ideas of Francis Forat, who was an engineer at the French Atomic Energy Commission in Cadarache, where they're building ITER. This guy was an engineer. In the 60s, he was working to make high-power lasers, solid-state lasers. And he had built these aluminum lanthanum oxide crystals, single crystals, and they wanted to be stoichiometric, but many times they turned out to be non-stoichiometric. And then when they were non-stoichiometric, instead of being transparent, they were red. So here's one. I'm sorry, I left it in French, but I know you all speak French here, so, or at least you had the class of French at school. I don't need to speak it. You can read it, maybe. So you can see that on the left side, it is red. I mean, my camera is not the best there is, but anyway, you look at it as red. Now, when you heat it up in deuterium or in hydrogen, it turns white. It's amazing. And you do the reverse. You heat it in air, it comes back red. I mean, I don't want to do that 10 times, but it's very reversible. So you can immediately see that the vacancies have been loaded. When you have vacancies, that's called color centers, it become red. Now, when you fill it, because lanthanum has a valency of 3, and why this is interesting, I mean, according to what he said, lanthanum has a valency of 3, aluminum has a valency of 3, they don't change valencies. So when you have vacancy, you have to put 3 hydrogen in order to balance the charges. So you have exactly what you need, a vacancy, controlled vacancies. Vacancies in palladium are difficult to make, but here you can control them. So these single crystals have been made in the 60s. I have a limited amount of them, and I'm saving them for future experiments. So I'm trying to make new ones, and so far I didn't really succeed. So that's why I didn't continue too much in this direction. But anyway, I have some recent results. This is my first type of calorimeter before the one I showed you, which was much more crude. So instead of having 50 thermocouples, I had only 17 or 18, only on one side. I was saving thermocouples. And they were not attached in series. I had to attach them from the outside. But it worked. And I got some results with that. Here's a curve of the temperature versus power input. And when there is no excess heat, when there's no voltage applied on both sides of the crystal, then I have the red curve. Now, when I apply voltage between the two sides of the crystal, I attract the deuterium on the cathodic side, and then, hopefully, you get more deuterium than the 3 that are expected when it is standard. Maybe you can go to 4 to 5. I don't know how far you can go. And I measured some good excess heat that way. Biological transmutation. Actually, I heard about biological transmutation in 1977, where I was in Berkeley. And at that time, I didn't know anything about it. Actually, I didn't know anything about chemistry. And I thought chemistry was test tubes, until I entered the field of cold fusion, when I realized you could do chemistry with physical instruments, like ICP machines, which we don't need to have chorus things, you know, that I hate. So as soon as I heard about cold fusion, actually I talked to Stan Ponce and Martin Fleischmann about it, and they knew about it. So they were really open to that too at that time. That was in '93, I think I talked to them. They knew about biological transmutations. So recently, during the past 20 years, I've done a number of these experiments, but the last one was done with algae, Spirulina. And again, I've seen changes, but not that well, because it's not that easy to do experiments with biological transmutation. So I've done increase in boron, in manganese, in sodium. I forgot, I don't know why, I'm stupid. I forgot to look at calcium, which is the one I should have looked at in the first place, but I forgot to do that. So there are so many applications of biological transmutation in the future for science, for diet, for agriculture, nuclear waste remediation. I mean, people have talked about it before me. And it's a very exciting subject. I'm looking for funding to do these experiments because I don't have the equipment, I don't have any ICP, and if I don't even have one, because if I have one, I have to run it, and it's very time consuming, so I want to have money to pay someone to do the analysis. Conclusion, scientific demonstration of cold fusion. I love to do that. I mean, people have done it years ago, so I don't think that I will bring a great contribution to the field. But I like the application for energy production. I think there is a good chance that by the next ICCF, we'll have almost commercial products. I'm pretty optimistic about it. And use of biological transmutation for nuclear waste remediation. This is important. There was a meeting on May 18 in Korea about that, so people are interested. They have a national program on that. I don't know how far it will go, but this is happening. So thank you very much for your attention. Thank you again.
Well, thank you very much, Jean-Paul. And double thank you for moving us back towards the time schedule. There is time for a short question or a comment. We're all relaxed. That's
sleeping now, after 1 week, Well, thank you very much.